Hello everyone. Today we're going to be starting 9.3. It's called continuous compounding. This is going to be something a little bit newer that's going to relate to the last two sections, which were on growth and decay. So we're still going to be talking about that, but it's going to kind of divert in a different direction a little bit. We're still going to be using the GeoGebra graphing website, so make sure you open that up. We still want that to be open here. So we're going to do some graphing on that. So for today's big question, is there a limit to how much you can earn in a bank account in a year, no matter how many times it is compounded? So we learned about this a little while ago where we said you could take money, you can invest it into a bank account or to some kind of investment, and if you let it sit there over time, you will generate interest and then you'll get more money. So we're going to take that formula, the old one we had, that was for general compound interest formula, and it was A equals P times 1 plus R over N to the NT. Now remember what these things mean. A was like how much you got after so many years. Here, P would have been your principal, how much you originally put into the account. And then we had our rate. So that's how much the bank or whatever you're investing in, that's the percentage that they're going to give back to you as an interest rate. The ends here, if you remember, that is how many times it is compounded in a year, which we'll talk about a little bit in this chart, but down below. If you remember, like we had quarterly and year or annually, we had monthly, things like that. So we chose a number here for N. And then lastly, T was your time in years. Hopefully you remember this kind of stuff. We're going to see, is there a limit to how much we can get based on how many times it compounds. So we're going to basically be increasing the ends here to see what happens. So we're going to do a very basic example and just start increasing the ends. And you'll see in this chart below of how we fill this out. Example 1. Suppose we had $1 to invest in an account and the bank will give you an interest rate of 100%, which is obviously not going to happen because that's a ton of money that would be given up. 100% is really high. We're just going to pretend to make nice, easy numbers. So we have $1 to invest, and the interest rate we're going to get is 100%. We're going to use the table below to see how much money we make as you increase the number of times it is compounded in 1 year. So we're going to do 1 year. Let's maybe label some of the stuff here. So T is 1 year. $1 is your investment, which is your P. Interest rate is 100%, which you got to move over twice, which is 1. As a decimal, right? You gotta move it over twice. So everything we have in here is basically 1. The only thing we're changing is how many times it compounds. So there's our general interest formula down here in this column. A is how much money we're making after 1 year. And then here we have the number of times it compounds. So we have annually, that's 1 time a year. So I even filled this out for you here. P is $1. We have 1 as your interest rate, which I already labeled up here. 1 is your number of times it compounds, 1 per year. And then 1 and the exponent is also the same thing because they're both ends. And then lastly, you would multiply this by 1 year, but we don't have to multiply by 1. I mean, you can if you want to put times 1 in there. But we don't have to do that because 1 times 1 is 1. So every single time we put that number in there, we're multiplying by 1 year, so it doesn't make a difference. Then when we calculate this, we get $2. Pretty simple. So let's go to the next one. I'm going to have to probably put this in my calculator to write it all out. I'll put this in the website, I think. Semi-annually means it's twice per year. So all I'm changing with this formula is just changing the number of compoundings, where N is. I'm changing it to 2 times a year. So that means the bottom number has to be 2 and the exponent has to be 2. And again, we're multiplying by 1 year, but I'm not going to write it. We fill that out, we actually get $2.25. So this is in 1 year, how much money you make. So the first year, we basically doubled our money. We went from $1 to $2. Next year, we went from $1. I mean, it's still in 1 year, but we're just doing it. We compound it twice in a year. Excuse me. So we go from $1 to $2.25. So we made a huge jump here by a whole dollar. But when we go to 2 times a year, it only went up by $1.25. All right, next one would be quarterly. Let's fill this one in. That'd be 4. So again, everything's staying the same. $1 investing, 1 plus 1 over 4 being raised to the 4th. And then you put in the calculator and get the answer. So let me go ahead and do that. 1 times 1 plus 1 over 4. And then we're going to raise that to the 4th power. Oh, I wasn't expecting that. Wonder if it would give me a decimal. There we go. So 2.44 right now. 2.44. So $2.44. So still not much more. It went from 225 to 244, but they did it even 4 times that year. They compounded it. They calculated your interest 4 times that year. So it's not going up nearly as much as it was. How about monthly? How many times a year is that? Monthly is 12. So we're going to plug in 12. 1 plus 1 over 12 to the 12th power. So basically I can just take the same thing I had in here. I just got to change these to 12s. 12 and delete that into 12. 2.61. All right. So we're slowly increasing here. Not by much again. So now they did it 12 times in a year, but we've only gone up to $2.61. So we haven't really accumulated much money, even though they're really increasing the number of times they're compounding it each year. All right, how about daily? Let's go even a lot more than just 12. We're going to do daily, which is 365 days. So it'd be 1 times 1 plus 1 over 365 to the 365th power. Again, just change that in GeoGebra. 365. 3.71. So now I think it's going to start, since it's less and less, so we only went up like, 10 cents or so. I'm going to go out a couple of decimal places so we can see the difference here. Let's go out a couple. 2.714567. This goes on for a while here. So we have $2.71. The reason I'm writing it out so many decimal places is because it's going to start getting close to a similar number as we see is going through. As we increase this number from daily to hourly to by the minute, we're going to start seeing some of these numbers set in place. So you'll see with the next one, if we go to hourly, what would that be? How do we get to hourly? If we have 365 days, we multiply that by what? 24 hours in a day. So that is actually 8,760. So again, filling this in, just basically copy and paste 8,760. 8,760. So maybe, I'm not sure if I can copy this stuff or not. I can copy and put it down here. That way we can see the difference on here. 8,760. 8,760. Oh, okay, so put it back up there anyway. So 2.71812. Do you see how close that is to our other number? I can put them on here. 2.71456, 2.71812. So it's changing a little bit, but some of these numbers are set in place. So now we actually have the 2.71 is the same. So we actually haven't gained any more money, but the decimal after that has changed. So now it's 2.71812. 12669. Whoops. 16. So it changes, but not until the third decimal place. So really, we're not gaining any more money. So at this point, it seems like there is a limit to how much you can gain, even if they compounded it hourly. So how do we jump by the minute? So we take that number, it's hours in a day, and how many minutes are an hour? That's another 60. So that's 525,000. And 600. So the last one we're going to do, I'm not going to go any further than this. 525, 600. 525, 600. So let's see how that changes. I don't know why I can't do multiple ones. 525, 600. And then 525, 600. Okay, got it. So 2.718279. So let's see how close that was to the new or old one. 2.718. So now the 8s are the same. It's just the next digit that's different, and so forth. So I probably should do it this way. So we have 2.718279249. Okay, so everything's the same for the first 4 digits, and then it starts to change. As we increase this number, the number of compoundings, these decimals start to set in place and give us a very specific number. As we make this bigger and bigger, and we change this to the bigger and bigger numbers, it ends up always being 2.7182, and then these specific decimals will stay in place. This is actually a new value that you have not heard before, probably, that we're going to start using. It's very similar to pi. It's a new value that we use a new symbol for. So this value grows closer and closer to a specific value we call E. Yep, just the letter E, but it stands for the specific number. So specifically, it is 2.71828, and it does go on forever, and it doesn't repeat. So it is an irrational number. Irrational number. And is used for interest that is compounded continuously. Compounded continuously. We only did by the minute, which is still a lot. Like, you know, if a bank were to compound something by the minute, that's a lot. If we would go to second or millisecond, it would keep making these numbers kind of the same, but then start forcing these decimals to be the same as well. So what we do know so far is that the decimal is 2.71828. It goes on forever, and these decimals keep setting in place the higher you go. So once you go as high as you can, which could be like infinite, they call it continuously, then there is kind of a set amount that you can get by using continuous. So it is actually named after somebody. It's spelled Euler. It is pronounced Euler. He proved that this sequence of numbers, like what we've been working with, you know, 1 plus 1 over n to the n, he proved that this, as you increase these n's, it approaches the number 2.718. So it approaches this number, 2.718, as we increase n. So as n increases. Which is what we were doing in this entire chart. We kept increasing the n value, and we can see it gets up closer and closer to this set number that they call E. So we're going to use this new letter. Think of E as just a number, just like pi is just a number. It's the same thing. When you see pi, you automatically know that it's 3.14, and it goes on forever. When we see E now, same thing. It's this number, goes on forever. You just have to know the number. So we're going to use this in a formula. Only when we see continuously do we use this formula. If something is compounded continuously. So if an amount P is invested in an account paying an annual interest rate R compounded continuously, the amount A in the account after T years is. So it's actually a really easy formula. It's easier than the one we've been using up here, easier than this general compound interest formula. It is A equals P, your principal, times E, and then it's all being raised. These two things are in the exponent. Your rate times your time in years. Some people like to call this formula the PERT formula. P-E-R-T, PERT. So we're going to use this anytime it says compounded continuously, instead of using these ones where it gave you like semi-annually or quarterly. Okay, so let's go to example 2. Katie invested $3,927.54 in a bond that pays 5.5% compounded semi-annually. After 30 years, the value of the bond will be about $20,000. How much would Katie's investment have been worth after 30 years if the interest were compounded continuously instead of twice per year? So they gave us all the information and how much Katie made by it being compounded twice a year, because it said semi-annually. We're going to use the same numbers here to see how much she would have gotten if it was compounded continuously. So since we're trying to do continuously, we're going to use that new formula. A equals P times E to the R times T. And we'll be able to put this, we'll fill in the numbers and then we'll put it into the website. So A equals, what's our principal amount? That's P. 3,927.54 times E. E is not a number we replace. We know what that number is. It's always 2.718, so on. And then our rate is what we need, 5.5%. This needs to be moved over twice. So 0.055 is R. 0.055, that's all in the exponent. Times, I'll put it around parentheses. How many years? 30, that's T. Let's put this all in the calculator at once in the website, because your phone probably can't do it like this. So we have, let's delete this up here, 3,927.54. I'll even put the times in there. E, it recognizes what E is. It's showing actually what it is down here. And I'm going to raise that to the power 0.055 times 30. And then hit enter. So this is how much money that she would have made had she done continuous compounding. So this would have been $20,450, whereas before she made about just $20,000. So an extra $450 just by doing compounding continuously. So as A equals 20,450.62. Not too bad to use that formula. So there'll probably be one or two like this that you have to do on your assignment as well. Make sure you understand how to do it, and that you can also use the website to get the right answer. All right, example 3. We only have 2 more examples left. So we're going to look at what this graph actually looks like. So the calculator does understand when you put E in the calculator, it knows what the value is. It knows how to work with it. Actually, if you see on here, E, there's actually an E button, just like there is a pi button. Same thing. So if you just actually type, let me delete this. If you just type in E, you can press the on your keyboard E, or you can do this button E, it doesn't matter. It will come up with the decimal form. So consider the function f of x equals e to the x, which is similar to the above interest formula. we're going to see what this looks like. We're going to graph it and do some things with it. Part A, is f of x an exponential growth or is it a decay? Which one do you think it is? So let's talk about this. So I think if we look at E, this is kind of like saying f of x equals, well, we know what the E value is. It's like saying 2.718 ... to the x power. Now, if you remember from a couple of days ago, or from the last couple of weeks, when we did exponential growth versus decay, what were we looking at? We were looking at this number specifically to see one of two things. If it's bigger than 1, then it's growth. If it's a number in between 0 and 1, then it's decay. So since E itself is a number bigger than 1, it is growth. So we should see the graph kind of starting off here and then shooting up like this, an exponential growth function. So part B, we're going to use the graphing calculator and graph it. So all I have to do here to change this is I'm going to graph it by pressing y equals E, type E, and then raise it to the x power. I'll hit enter. Oh, it went away. Maybe I should not hit enter. Y equals E to the x. There we go. So you can see it. We know it was going to be a growth function anyway. So it's starting off down here and then shooting up pretty quick. And you can zoom out on it and see this is definitely a growth function. It's going up pretty quickly. So answer the following, and then I'll also do a little sketch down here. We can see that domain is and range are the same for growth functions. If you remember what domain and range are, domain means how far you can go left and right. So it goes on forever down here to the left. I know you can't really see, but this is getting closer and closer to this point, the x-axis, and it goes on forever to the right. So that means the domain is all real numbers. The range, the lowest y value is it goes down close to 0 but never touches the x-axis. So it starts bigger than 0 and then goes up forever. So the way we said that was y is greater than 0. I'm not sure if you remember, we could also do the 0 to infinity symbols. I don't know if you remember doing this. Either one is fine, but I think I've been using the y is greater than 0. The y-intercept, where's across the y-axis, that's clearly, it even labels it for you at 1. So that'd be y equals 1. X-intercept, well, we just talked about that. It does not come down and touch the x-axis at all. You can zoom in, keep zooming in. It actually gets closer and closer, but it never touches. So x-intercept, there is none. Growth factor, if you remember what the growth factor was when we talked about the original, no, not that. It was f of x equals a times b to the x. The growth factor is always the number that's close to the exponent x. So in this case, it's 2.718. Or you could just write e. Either one's fine. And then the asymptote, where does it not touch on the graph? That would be the x-axis. It comes down, gets closer and closer, but actually does not touch the x-axis. That's called the asymptote. Just like the other growth exponential functions that we did a couple weeks ago. I'm going to just do a basic sketch of it as best I can. So it's going to cross at 1. It's going to go up like this forever and slowly go down like this. A little basic sketch. So f of x equals e to the x is a growth function. Now you can get it to be decay. So how does that happen? So in this little box here, how can we tell if e to the x is growth or decay? Very simple, actually. If you look at the exponent and it happens to be positive, so if you look at this exponent, it's just x. There's really no number there except for you could say it's 1x. But if that's a positive number, then we get growth. If the exponent is negative, doesn't matter what it is, in the exponent, they could just put a negative sign there, right? If it's just negative x, if that exponent is negative, then the graph is decay. So why does this happen? Why does it matter if it's positive or negative? So for one, the easy one that we talked about, why is it growth? When you see e to the x, that's the same thing as 2.718 ... to the x. That's easy to see that's growth. We said if it's over 1, then it's growth. The hard one is to see if it's negative. As soon as you make it a negative x, or it doesn't matter what number is up there, you can have like a negative 5x, just like you could have a 5x up here. We haven't really messed with putting different numbers in the exponent there, but as soon as you have a negative x, what you have to do is you have to deal with the negative exponent. And how we do that is we always take the number, remember, and put it over 1. And then what we do is we flip this to make that exponent positive. If you remember doing this at all, that's the same thing as 1 over e to the positive x now. So we force it to be positive by flipping the actual fraction. So then we look inside here and say, well, what's our growth factor? 1 over e, what does that mean? That's 1 over 2.718 to the x. And what is 1 over 2.718? Let's just check that out. 1 over 2.718, and it goes on forever, but let's just see what this looks like. That's 0.3679. So this is the same thing as 0.3679 to the x. So is this growth or decay now? Well, if it's 1 over 2.718, which is 0.3679, it's between 0 and 1. Now you have decay. So I kind of went off and tried to show you that the original one is always going to be growth, because it's always that number, 2.71, which is bigger than 1, so it's always growth. But as soon as you put a negative exponent there, you have to flip the fraction around to make it positive. So in doing so, that makes the decimal become a number between 0 and 1 every time. So you don't need to know all that. I just want to show you what it looked like. The important thing is, can you determine whether the exponent is positive or negative? So for the last example here, state whether each equation is growth or decay. All you're looking at is the exponent. Since we have a negative number up here in the exponent, that means it is a decay. For part B, y equals e to the 4.5x. It's a decimal, but I don't really care what the decimal is up here. All I care is a positive or negative. So positive means growth. And the last one, exponent is negative. That means decay. So I'll throw a couple of those on the assignment as well. Those ones should be pretty easy. You can also see what they look like. Maybe I'll just graph one of these. Let's see what e to the negative 2x looks like. And then I'll be done. E to the negative 2x. So you can see it. There it is. And you can see it's decay. It's going up really high, and then it's going down pretty low here. So that's all you have to remember. Negative exponent gives you decay. Positive exponent gives you growth. So if I change that e to the positive 2x, now we get the same thing. It's just now it's growth. See? Makes a big difference in how the graph is put on there. All right, so that was week 8. Don't forget to go through this with the website and use the website again on your assignment. And we'll see you next week.